Hi guys, welcome to my YouTube channel. Here we are mostly going to talk about some competitive programming content, but maybe in the future we are slightly going to change the whole concept. And let me introduce myself. My name is Radoslav Dimitrov. I have been doing competitive programming for quite a long while, and today I'm going to introduce you to a concept called virtual or auxiliary trees, which are used to solve some data structures problems. They may be complicated, but also some easier problems can be solved with this technique. And let's get right into the point. So let's first introduce the problem we are gonna solve, and let's imagine we have n less than 100,000 vertices. Yeah, we have like a tree with n vertices, and also we have q queries, where q again is less than 100,000, where each query is represented by a set of vertices that's called v1 until vk, and we have a bound on the total number of vertices in all queries, which is again less than 100,000. So let's see what each query will represent. Imagine the given tree is this thing, and let's imagine some random query that is represented by these four red nodes. And the answer to this query will be the sum of distances for each pair of different vertices. So in this example, it will be the distance between this vertex and this vertex is 6, then between this vertex and this vertex it's 5, and finally between this vertex and this vertex it's 3. So the answer to this query will be the sum of the three numbers, which is apparently 14. And we have to answer q queries of this type, but we have the constraint of the total number of vertices, which is again less than 100,000. More formally, we are asked for a certain set of vertices to compute the following sum, which is we iterate over each different pair of vertices and we sum the distances. So now I'm gonna leave you to think about it for a bit, and after that I'm gonna present the different solutions to this problem, but we'll mostly focus on the solution which is using the technique called virtual or auxiliary trees. So first, I'm going to talk about two approaches, which are pretty simple. The first one being the ON approach for finding the sum of lengths of paths between all pairs of nodes. This is a well-known problem, and it can be solved with either dynamic programming or another approach would be to consider each edge and finding the number of paths in which it exists. Both of this can be done in linear time over the total number of vertices. However, this isn't very good because we can have quite a lot of queries where each query will have just 3 or 4 nodes, and this way we will have to iterate over the whole tree for all queries, and this isn't ideal, and that's why it will time limit. Now the second approach, it will be a k-squared approach, and basically it will just consider all pairs of nodes in the current query, and it will find the sum of the lengths of the paths. I mean, basically we want to compute the sum. We can iterate over each pair of vertices, and then we can find the distance between a pair of vertices by doing LCA or just some other pre-compute. Like, we can find this distance in ON by pre-computing the depths and then using LCA, and this way we can find the distance in constant time. Hence we have the approach which works in k-squared time. So alright, we have these two basic approaches, and if we combine them by running the second approach when we have just a few vertices, and the first approach when we have quite a lot of vertices, we can get an s square root of s approach, where s is the total number of vertices in all queries. More formally, if we have more than square root of s vertices, we'll run the ON solution, and if we have less than square root of s vertices, we'll run the k-squared solution. And this way we can get a decent solution. However, that's far from the best one we can get. And now I'm gonna start talking about the main approach, which is the virtual tree solution, which will work in n log s time. Alright, so as I still haven't mentioned what the virtual tree will actually represent. Let's imagine we have this tree where again the red vertices are the ones which are for our query, and the other vertices are the ones in the tree. Now let's consider the blue vertices, which will be the needed vertices to represent a compressed tree of all paths. You can convince yourself that now all important paths, by important I mean a path between a pair of red vertices, will have its topmost vertex, which is the LCA, certainly marked in either red or blue. In this particular case, it will be definitely marked by blue. And in other words, we can think of the blue vertices as the LCAs of any pair of red nodes. And you can convince yourself that any path between a set of red nodes will go through an LCA. That's just because if we have a set of all LCAs, all k-squared LCAs, then all paths will have their LCA in the set. However, actually before that, let's see how this tree will look like. I mean, it will look like that, because that's the blue nodes and the other nodes are the red ones. We should know that this tree will be weighted because some nodes will be compressed in it. For example, this node will be compressed in the path between this blue node and this red node, and hence the weight of this edge will be 2. Also, we can note that some of the vertices will be excluded from the second tree. For example, this node and this node aren't present in this tree. I mean, they aren't present in any way. As for example, this one is presented in a compressed form as in this age. So the most important thing about this compressed tree is that it represents the whole information when we want to answer some queries which are based on a subset of the nodes of the whole tree. And why the whole virtual tree approach is good is because the number of vertices in the compressed tree will actually be at most 2k minus 1, which is OK vertices, which you can see it's linear depending on the number of vertices we have initially. And that's because, as I said, here one may think that we have actually k-squared needed vertices to represent all paths. However, the needed additional blue vertices, you may call them like that, is actually just k minus 1, and it's not quadratic, it's just linear in the number of total nodes. That's because we will have at most one vertex for each pair of consecutive red nodes based on their DFS time. If you aren't familiar with what DFS time is, I'm gonna link it in the description of this video. You can read it. There are a bunch of tutorials on Codeforces or some other platforms like Geeks for Geeks and etc. Alright, so I hope you will be convinced that we'll have an additional just k minus 1 nodes, which are LCAs of. So my video just stopped at the point where I explained why the number of additional nodes will be k minus 1, but briefly we'll have at most k minus 1 nodes additional, because every LCA will be, every needed LCA will be an LCA of 2 consecutive nodes based on their DFS time, just because of the definition of DFS time. And we can prove the contradiction by considering some LCA which happen to be created by 2 nodes which are not consecutive in the DFS time of the important nodes. Then if we have a node which is between them, it will have the same LCA, hence we have a contradiction. You can prove it on paper and convince yourself. But yeah, that's the main observation. Alright, so now let's go to the algorithm, and I'm going to show you how to create this virtual tree which will be this weighted tree in k log time, because we'll need one sorting. If we have the vertices in order of their DFS time, the whole approach can be done in linear time, but I'm gonna introduce you to the general case, and let's get right into it. So now let's go to the algorithm. Basically, as I already said, we will have a set of vertices, which are k, and after that we will need to extract additional vertices, which will be pairs of which will be LCAs of pairs of consecutive vertices based on their DFS order. So basically, the first part of our algorithm will be we sort our vertices by their DFS time. After that, we will add the needed LCAs to our list, which is at most k minus 1 vertices. And finally, we'll sort all of these vertices again. And this way we'll get the important vertices in our tree, virtual tree. So this step will be in k log time, because we have two sortings. If we have our vertices given in the order of their DFS time, the approach can be done in linear time, but in the most general case, we will just have them as some indices of the vertices, and we'll have to sort them by their DFS time. So now the second part of the algorithm will be the actual building of the tree, and we'll actually maintain a stack which will represent a slope of the vertices which haven't been considered yet. I'm gonna explain it now, and then we'll go through the vertices by their DFS time, and we will change the stack and add some edges to our virtual tree. Alright, so basically, let's consider a stack. The bottom of the stack will be on top, and the top of the stack will be on bottom, which is very counterintuitive, but it's, in my opinion, easier to explain, and I'm gonna talk in these terms. Basically, let's have a stack which will be the black nodes here, and we'll have the for link invariant. The topmost vertex will be a child of the one before it, and so on. Basically, the stack will represent a chain of vertices such that the topmost one will be a child of the one before it, and so on. Now let's consider a vertex, which is the one in red here, and we know that it has DFS time greater than the DFS time of all vertices here, because as I said, we'll go through the vertices in order of their DFS time. And now we want to change the stack in such a way that we'll include the red one, the new red node in it, and we'll exclude the previous nodes which won't matter anymore to the structure of our virtual tree. So basically, the first step is we look at the top of the stack, which will be this vertex, and we look at its parent. If the top of the stack is not a parent of our red tree, basically it's not, we can add the topmost vertex as a child of its parent, which is the previous vertex in the stack, and we can remove it. Now we can consider the case of one less vertex in the stack, basically in this case. That's because we won't ever need this topmost vertex anymore, as we can just consider the rest of the stack. That's because the new vertex, the one in red, is in a narrow subtree, and hence this vertex can be just added to as a child of the previous one. And we'll do this until we get to a vertex which is a parent of the newly created vertex. Not the newly created, but the one we are currently considering. So basically, we are gonna do this until the case where the topmost vertex is a parent of the new vertex. And in this case, as I already mentioned, we'll have two subtrees. the one which we already removed, which won't matter to the next parts of the tree, and we can simply add the newly created vertex as a new top of the stack. So basically, we just remove some of the vertices in the stack, and then we add the vertex we are currently considering to the top of the stack. And you can notice that the invariant I initially mentioned, the fact that the topmost will be a child of the one before it and so on, will keep in this whole process. So why is this important? Well, this way we can create this virtual tree in linear time. So then the final part will be basically to solve our query in linear or sublinear time based on our new tree. You can think of it as we have already created a new tree in OK time, actually OK log, but let's say it's linear or sublinear in K. And now we have just another tree with some weights for the edges that has 2k minus 1, at most 2k minus 1 vertices. And we can just solve the problem on it in the same way as we initially introduced our ON solution. Like basically, we'll have a new tree which will have a linear time based on k vertices, and we can solve the problem in this way on it. And then the complexity won't be ON, but it will just be OK. Hence, we'll have the wanted S log S solution. And now I'm gonna go to the part of writing out the implementation, which is actually pretty simple. So now let's go to the final part, which is the implementation of the approach. And before that, I have prepared the test case, which is the tree we talked about before that. And also we have just two queries. Basically, that's the tree we talked about before. And then we have the initial query, which was the 3 vertices over there. And finally, we have another query, which has 2 vertices. And the vertices are again, they were from the red set I was mentioned before, and it's the vertices which had distance 3. So the answer to this test case should be 14 and 3, if I'm not mistaken. I haven't checked it before, so we'll see. So let's write the implementation. Alright. There's some default code which doesn't really represent anything for this problem, but let's first have the tree as an adjacency list. So we have n vertices. First we read the vertices, then we go over the number of edges, which is n minus 1. There's we will input the current edge, and then we'll add this edge to the adjacency list. And now, probably I'm gonna speed forward this part where I'm gonna implement the LCA, because for the virtual tree approach we'll have to have LCA, and you can just probably there'll be a skip to somewhere button here, and I'm gonna speed this part up. Okay, so here actually I'm gonna stop the spinning up. This part, which is a function upper, it will be represented by 2 vertices which are U and V, and it will denote where U is above V in the DFS tree. This can be easily done if we have the start and end time of the vertex. The start and end time, just to mention it now, it's basically it basically represents the start time represents the DFS order, and the end time represents the DFS order of the maximum DFS order of some vertex in the current subtree. And then a vertex is above another vertex only if and only if its start and end time overlaps the start and end time of the outer vertex. Actually, if it covers the whole interval of the bottom vertex. In other words, u is above v if start of u is less than or equal to start of v, and end of v is less than or equal to end of u. Basically, the interval of u is, it just covers the whole interval of v. You can actually note that here we can write start or end, it doesn't really matter, because no two intervals intersect. We can just have one interval completely covering another one. We can never have the case where one interval just partially covers another one. We can prove this easily. Alright, so this function is pretty important not only for the LCA but also for the next part. And now again I'm gonna probably speed up the whole implementation. Alright, so we're back, and right now we implemented the LCA, and let's now start with writing the interface, not the interface, but like the part where we go through the queries. So we have Q queries, and we will go through each one of them. So we have Q queries. Now we should input the k, which is the number of vertices, as we already mentioned like a bunch of times. Let's have the vertices for the current query in a vector, and basically while k decreases, let's have some x, we inputted, and we add x to the back of the vector. And now let's have root. So we have virtual tree root, and now is equal to virtual tree of the current vector. And now we will have solve for the current tree. So this solve method will be basically the solution when we already have the newly created tree. We'll implement it after that. So let's have solve of root. We are gonna implement this after that, just to remove this warning because it's kind of annoying. I'm just gonna return it here. And now let's have int virtual tree vector int vertices. This will basically create the virtual tree. So first let's have a compare operator to vertices, which will just return them in order of their DFS time. It's as simple as this. And now let's sort them all. All is defined for for vector that begin and comma vector that end. It's just for simpler implementation. Okay, so we have sorted all vertices. Now let's go through and let's have k, which is equal to the size of the vertex. Again, size as z of a vertex is the size, and let's go through all of them, actually through all pairs of consecutive ones. New vertex, like this is a new vertex, will be equal to the LCA of vertex and the next one. So it's just this one, this thing, and we will just add it to a vertex, like the vector of the vertices. As simple as that. Now, as in the first part of the algorithm, we will again sort all vertices. However, I realize that here I missed a part where we will erase the vertices that appear more than once. So basically we'll do vertices.erase. We'll erase the vertices that appear more than once. So we can do this with one unique if we implement this in C++. So this should create a vector of all vertices that are needed. And so far this is okay. Block, because we have a sort. Alright, so now this is the most important part, and let's have a vector which will represent the stack of the vertices. Initially, the stack will contain the 0th vertex here, which is just a vertex of 0. Now what we want to do is we want to go through all vertices, except for the first one, because it's just it, and we have already added it to the stack, and basically this will be starting from 1 until size of the vertices e++. And what we want to do is we want to somehow change the stack here. Alright, so first of all, let's have this is the main part of the algorithm, so let's think what we'll have to do here. Basically, we have a stack of the vertices which may be the parent of the current one, which is u. Let's have u as our current vertex, so u is vertex of e, and let's have our stack, like the stack is the stack of vertices. If the top of the stack is if it's not a parent of our current vertex, we can simply remove it. So something we can actually do is, if size of the stack of vertices is greater or equal to 2. I'm going to explain why we need greater or equal to 2 in just a bit. You'll actually see it in just a second. And if we don't have, so as I already said that we'll need this upper function, and if the stack of vertices, that back, which is the last thing in the stack, if the top of the stack is not above our current vertex u, we can actually remove the stack of vertices that back. And how do we remove it? We can simply write it as stack of vertices that pop back. And I mentioned that we actually would need to add the edge between this stack of we'll need to add the edge between the stack of vertices and its parent, which is the previous thing in the stack. So basically we'll have to add edge here. So let's represent the virtual tree in this structure, which will be vector of virtual tree of maxi. Let's call it actually in a better virtual tree. I'm just going to call it adjacency of VT, which comes from virtual tree, and we're going to add adjacency of virtual tree of stack of vertices, size of stack of vertices minus 2. Here, as I said, you're going to see why we need the greater or equal to 2. Here we will need minus 2 because this thing will be the parent of the current back. So basically this is the parent of the node we are gonna pop now, and we're gonna add the node we are popping as a child of this one. So here we add stack of vertices that's back. And here I missed an S. Okay. I missed something else, apparently. Again, one additional S. Maybe I should have called this stack in some other way, but whatever. Alright, so we can also notice that if the stack contains one element, it will contain only the topmost vertex. Why? Because the topmost vertex will actually be the one with the smallest DFS time. And we actually added it in the beginning, over here, as you can see. Here we added the first vertex, and it will have the smallest DFS time, hence it will be the topmost vertex in the ones we are gonna consider. Alright, so here we already removed the vertices we don't need anymore, so we simply need to add the new vertex as the bottommost vertex in the stack, which will be done by stack of vertices that push back the current vertex, which is u. And that's everything. Actually, not completely everything, because after the whole process, maybe we'll have some slope, so we would need to remove everything from the slope. So while size of the stack of vertices is greater than 1, or greater or equal to 2, let's have it similarly to the one above, if this is greater or equal to 2, we'll do basically the same thing, as we know that the parent of the bottom of the topmost thing in the stack will be the previous thing in the stack, so we add it as a child, and then we just pop the topmost thing in the stack. So you can actually just see that after this point we'll have exactly one vertex in the stack, and we can just return it as the root of the tree, because we know that it will be the first vertex we added here. And why, you may not see it immediately, it's pretty simple, but still, I'm gonna mention it. We added here because, and not just in the end, because this way it will be easier to add it as a parent of some of the things in the stack. Like, just to make the implementation easier, we add it in the beginning to the stack and then just return it. And so in the end we just return stack of vertices that back, because it has, we can also say 0 because it has exactly one element. So this is the whole implementation. It's pretty simple, I would say, after implementing LCA, which is also pretty simple to implement. And now let's write out the part where we solve our problem. This is like the virtual tree part. Now we have our virtual tree as an actual tree. Some part I actually forgot to implement, so I'm gonna speed up the video now. Is the depth of the tree. Why do we need it? Because actually this tree here will need the weights of the trees. But that's not very hard. Actually, I'm not even gonna speed up the video. I'm gonna have some depth array here in this part, and we'll have depth of v is equal to depth of u plus 1. And initially in the LCA pair compute, we'll have depth of root equal to 1 or to 0 or 1, and it doesn't really matter. We are ready. Perfect. Okay, now the final part, which is how to find this solve function, which will just do some, I'm gonna do it recursively. So basically the virtual tree returned the root of our tree. So now what we can do is we can pre-compute. Okay, before that we are gonna need to mark some vertices as important or not. Well, important. And important will be the ones which are given in the query initially. So here we're gonna do important of x is equal to true. Also, because we are using a global array, after that we'll have to remove the important vertices. So after, actually not here, but over here, So here we are gonna do important of x is equal to false, because we are using a global array and we don't want to confuse every query with the previous one. And now the vertices in our query are in the important array. Let's have subtree count, which will represent the number of vertices in every subtree which are important. Basically, subtree count of root. Actually, here this will be our subtree root, because solve will be recursive. Subtree root of u will be equal to important of u, and basically now we are gonna consider the root. Also, we are gonna have another parameter which is parent. This is the parent in the virtual tree, and basically if the parent is not equal to -1, we are gonna see the contribution of the current edge. And how we are gonna do this? We know that the weight of this edge in the virtual tree is depth of parent minus depth of u. Actually, the opposite. It's depth of u minus the depth of parent. And what we are gonna do is we are gonna multiply w minus the... Alright, then we also need answer, which is equal to 0. So answer will be increased by w multiplied by the number of paths which contain this edge, which it's a compressed edge, so it's technically a couple of edges, but in the compressed tree it is just one edge, and the number of paths which contain it will be 3 of u. We'll actually need this after that, so we'll have this after computing this subtree. Basically, after computing subtree count, we'll have to add w multiplied by subtree count of u multiplied by total count minus subtree count of u. What does this mean? Total count will be an integer. We'll need one long. Total count will be the total count of important vertices, which is we are gonna compute it here, and total count is size of vertex. Basically, it's the total number of important vertices. And now the final part is basically we need to compute this. We iterate over the adjacency versus in the virtual tree. We know that v is definitely a child of u, so we just call solve of this child. So we solve v with u, and here basically we solve v with u being parent, and then we add subtree count of u is increased by the subtree count of v. And if I'm not mistaken, this should work. Okay, it compiles, but I forgot to copy the test, so I'm gonna copy the test. You can again see it if you want. It's basically the test I showed in the beginning. So let's go here and let's hope it works. Does it work? Apparently it doesn't. Oh, it does, but apparently right now, because of the video, it is kind of slow, but also it's wrong. So now let's see why it's wrong. I'm probably gonna speed it up before just seeing it. That shouldn't have been like that. Unfortunately, it is. So the DFS time is correct as far as I'm concerned. Yeah, the LCA also looks fine for VU. Does it actually look fine? Yeah, it is. It should be fine. Yep. We compute it here. So actually, let's see what will actually the DFS tree look like. So we are gonna represent some south edge from parent to you. It's so slow because of the video and my computer. The Macs aren't so fast, surprisingly. And alright, so we have 1 as a root, which should be the case. Then from 1 we have an edge to 5, which indeed is the case. Alright, so far it looks fine. I guess we have the virtual trees look fine. I guess we have made a small mistake somewhere here. Okay, so let's print the subtree count, U, the total count, and the W. We have the print from above to see why it's wrong. Okay, so we are considering 5 to 7. No, that's not convenient enough. I'm gonna print it here. And that's because we are calling the DFS before that. Okay, so let's see again. Yeah, that's definitely what I wanted to print. Alright, so 5 and 7, we have 1, the total count is 3, and we have 0, which isn't what we want. Basically, the W is computed in the wrong way. Okay, let's see what is the problem here. Oh yeah, so that's a pretty common mistake when you're adding things. Basically, I was computing the depth after calling the recursion, and that shouldn't be the case. Wow, this video really creates some very weird errors. Alright, so you can see 14 here and 6 here. Apparently, I think in the beginning I said 3, but it should be 6 if I'm not mistaken. Let's see. Probably it's 6 if I'm not mistaken. No, I'm pretty sure it shouldn't be 6. So we have 2 edges, 2, 5 to 7. We have 2 vertices. Alright. Oops. From 5 to 7. But why is this considered twice? That's pretty. Oh yeah. Okay. Yeah, it should be 3 as I said. That's another problem which we had. I think it's more useful to talk about some problems you may face while implementing it. Basically, what we didn't consider is the edges we have from previous queries. We need to empty this adjacency of VT vector. Alright, basically, we already computed 1 query. The first one was computed well, and for the second query, we had the problem that we kept the edges from the first query which we added in adjacency VT. So that's why we are gonna remove them. We know that the important vertices are right now in the vert, so we are basically just gonna iterate over all vertices in the vert, and we are clear the adjacency of VT. Okay, so let's compile it again. This is already yeah, great. I'm not sure for whatever. did this error so many times. Okay, you can see it here. It's 40, and the next one is 13. Just to convince you, we already have it implemented in virtual tree. Let's run it with test.n, and the answers are 14 and 13. And we have implemented the thing correctly, finally. Let's look at it again and just briefly explain each part again. So the first function is the reading of the tree. That's trivial. Then this is the LCA. We use binary lifting to compute the LCA. This is the upper function. Basically it says whether u is above v. It can be computed with DFS time. Then LCA is basically just the LCA of the two vertices. It does binary lifting. First of all, we consider whether u and v are, whether u is above v or v is above u. After that, we know that both of them, neither of them is a parent of the other, and so we can just leave the first one until it's not a parent of the other one. And this way, if we do the binary lifting from the topmost power, we know that the LCA will be the parent of the vertex, like the zeroth parent. And then we just pre-compute the LCA. So the vertical tree, as I said, compare sorts by the time, which is like the DFS time. Then we extract the new vertices. After that, we sort them again and remove the ones that appear more than once. Like, we just make the unique vertices. If something appears twice, we will keep it just once. Then we clear the virtual graph, as you already saw this error, where the virtual graph from the previous step keeps for the second one. After that, we add the first vertex, like the topmost one. We maintain the stack, we remove the topmost, and we add one edge. Then we add the topmost to the stack. Then we have, in the end, a slope, and we add the edges until we have just one vertex in the stack, and this vertex will be the top of the stack. And then the recursive solve, answer will keep the answer. Then we compute the subtree, the number of important vertices in the subtree. We increase the answer with the answer of the other subtrees, which are children of the current one. We also compute the subtree count value, and then if an edge from the current vertex to its parent exists, like basically if we aren't considering the current root, we'll just get the weight of the edge to the parent, which may be more than one vertex, that's why it has weight, and we'll see in how many paths it exists, which is the subtree count of the current vertex multiplied by the total count of vertices minus the subtree count, which is the number of vertices, the important vertices which aren't in the current subtree. Basically, that's the number. That's the number of edges in which the current vertex exists. Okay, so then finally we pre-compute it, we read Q, and we just create the important vertices. We created the vertical tree, we compute the total count, and then we just print out the answer. And that's everything. I hope you enjoyed this part, and I guess that's the video. If you have some feedback, leave it. I would be grateful for just any feedback, and I hope you enjoyed it. If you have some suggestions for a next video, or if you have suggestions for me to not create any videos anymore, you can feel free to just comment it. I'd laugh if you subscribe to my newly created channel, and I guess see you next time. Bye.